After learning about Clairaut's theorem, check out the different complications on figuring out higher partial derivatives. Welcome to Differential Calculus. The first example requires all the second partial derivatives from the function z is equal to x raised to 4, y raised to 5, minus 3x times the root of y cubed, plus x raised to 6, minus sine of 3y. In order to find the second derivatives, it is quite obvious to start with the first order partial derivatives of the function. Since there are x and y variables, it is expected to have two first-order partial derivatives. We start off with finding the first-order partial derivative of the function with respect to x. The partial derivative of z with respect to x is therefore taken as the constant of the first term, y raised to 5, multiplied by the derivative of x raised to 4. Then subtract the constant of the second term, 3 root of y cubed, times the derivative of x. Then add the derivative of x raised to 6 minus the constant of the last term sine of 3y times the derivative of 0, which is basically 0, and dx over dx is 1. Simplify the function further to get y raised to 5 multiplied by 4x cubed times the derivative of x minus 3 root of y cubed plus 6x raised to 5 multiplied by the derivative of x. Again, dx over dx is 1. So the partial derivative of z with respect to x is 4x cubed y raised to 5 minus 3 root of y cubed plus 6x raised to 5. Now with the first derivative already figured out, continue working on the second derivative with respect to another x, which becomes the first term's constant, 4y raised to 5, multiplied by the derivative of x cubed, minus the constant 3 root of y cubed times the derivative of 0, plus 6 times the derivative of x raised to 5. The second term then turns to 0, and the reduced function is 4y raised to 5 times 3x squared times the derivative of x plus 6 times 5x raised to 4 times the derivative of x, where again, dx over dx turns into 1. So the second partial derivative of z with respect to x is 12x squared y raised to 5 plus 30x raised to 4. The other derivative is the one with respect to y, making the first order derivative turn into 4x cubed times the derivative of y raised to 5 minus 3 times the derivative of y raised to 3 halves plus 6x raised to 5 times the derivative of 0, which basically zeroes out the third term. So the function becomes 4x cubed times 5y raised to 4 times dy over dy minus 3 times 3 halves of y raised to 1 half with the derivative of y. So the second partial derivative of z with respect to y and x is 20x cubed y raised to 4 minus 9 half of root of y. The first derivative order is already complete until its second derivatives, so we go back to the original function and solve the other first-order derivative with respect to y this time. dz over dy comes as x raised to 4 multiplied by the derivative of y raised to 5 minus 3x times the derivative of the root of y cubed plus y raised to 6 times the derivative of 0 minus the derivative of sine of 3y. Work further on the derivative to get x raised to 4 times 5y raised to 4 times dy over dy, minus 3x times the derivative of y raised to 3 halves, minus cosine of 3y times the derivative of 3y. dy over dy is 1, so the derivative of 3y with respect to y is 3. The function is simplified further as 5x raised to 4, y raised to 4, minus 3x times 3 halves of y raised to 1 half times the derivative of y, then subtract 3 with cosine of 3y. Finally, the partial derivative of z with respect to y is 5 x raised to 4 with y raised to 4 minus 9x root of 4 over 2 minus 3 cosine of 3y. With the first partial derivative already determined, we move to the second order derivative with respect to y. In here, we get 5x raised to 4 multiplied by the derivative of y raised to 4 minus 9x over 2 times the derivative of y raised to 1 half, and subtract again 3 times the derivative of cosine of 3y. After differentiating the first level, we arrive at 5x raised to 4 times 4y cubed multiplied by the derivative of y, minus 9x over 2 times 1 half of y raised to negative 1 half multiplied by the derivative of y, minus 3 times the negative sign of 3y with the derivative of 3y. dy over dy is 1 and d of 3y over dy is 3. So the second partial derivative of z with respect to y is 20x raised to 4y cubed minus 9x over 4 root of y plus 9 times sine of 3y. Then lastly, take the second partial derivative of the function with respect to x, giving 5y raised to 4 multiplied by the derivative of x raised to 4 minus 9 over 2 root of y times the derivative of x, then subtract 3 cosine of 3y times the derivative of 0. dx over dx is 1, and the last term also becomes 0. Thus, the derivative becomes 5y raised to 4 multiplied by 4x cubed with the derivative of x minus 9 over 2 root of y. Again, dx over dx is 1, giving the second derivative of z with respect to y and x as 20x cubed y raised to 4 minus 9 halves of the root of y. To summarize the derivatives for the function, we have dz over dx as 4x cubed y raised to 5 minus 3 root of y cubed plus 6x raised to 5. Its first order counterpart is the derivative of z with respect to y, given as 5x raised to 4 y raised to 4 minus 9x over 2 root of y minus 3 cosine of 3y. Going back to the first derivative, we get the second partial derivative of z with respect to x as 12x squared y raised to 5 plus 30x raised to 4. And the other is the second partial derivative of z with respect to y and x as 20x cubed y raised to 4 minus 9 half of the root of y. The other pair of second derivatives are the second partial derivative of z with respect to y as 20x raised to 4y cubed minus 9x over 4 root of y plus 9 sine of 3y. The other is the second partial derivative of z with respect to y and x, showing 20x cubed y raised to 4 minus 9 half of the root of y. Take note that the two second partial derivatives are the same, showcasing Clairaut's theorem. The next example requires the sixth partial derivative with a combination of independent variables of the function x raised to 4 y cubed z raised to 6 plus x cubed y z raised to 4. For the del notation, the first order derivative starts on the right. In this case, the first order derivative is with respect to x. So the function is differentiated as y cubed z raised to 6 times the derivative of x raised to 4 plus y z raised to 4 multiplied by the derivative of x cubed. Working on derivatives, we get the constant y cubed z raised to 6 times 4x cubed with the derivative of x plus y z raised to 4 times 3x squared with the derivative of x, where dx over dx is 1. Thus, the partial derivative of f with respect to x is 4x cubed y cubed z raised to 6 plus 3x squared y times z raised to 4. After the first partial derivative, check which to use for the second order. In here, note that the next independent variable to work the partial derivative with is again x. So take the second partial derivative of f with respect to x. Having 4y cubed z raised to 6 times the derivative of x cubed plus 3y z raised to 4 times the derivative of x squared. This is simplified as 4y cubed z raised to 6 times 3x squared with the derivative of x plus 3y z raised to 4 multiplied by 2x with the derivative of x, where dx over dx is 1, giving the second partial derivative of f with respect to x as 12x squared y cubed z raised to 6 plus 6xy times z raised to 4. Continue to the third derivative, which is with respect to y, being 12x squared z raised to 6 times the derivative of y cubed plus 6x times z raised to 4 times the derivative of y, where dy over dy is 1. So the simplified solution becomes 12x squared z raised to 6 times 3y raised to 2 with the derivative of y plus 6xz raised to 4, where again dy over dy is 1. So the third partial derivative of f with respect to y and x is 36x squared y squared z raised to 6 plus 6x times z raised to 4. For the fourth derivative, the function is differentiated with respect to z. The differentiation goes as 36x squared y squared times the derivative of z raised to 6 plus 6x times the derivative of z raised to 4. This continues as 36x squared y squared times 6 z raised to 5 with the derivative of z plus 6x times 4z cubed multiplied by the derivative of z. This time, dz over dz is 1. So the fourth order derivative, which is with respect to z, y, and x, is 216x squared y squared z raised to 5 plus 24x times z cubed. A few more differentiation to go. Let's move to the fifth differentiation, still with respect to z. We start with 216x squared y squared with the derivative of z raised to 5 plus 24x times the derivative of z cubed. This is simplified as 216x squared y squared times 5z raised to 4 with the derivative of z plus 24z with 3z squared times the derivative of z, where dz over dz is 1. So the fifth partial derivative of the function with respect to z, y, and x is 1080x squared y squared times z raised to 4 plus 72x with z squared. To complete the requirement, we move on to the sixth partial derivative of the function, this time with respect to y. Start with 1080 x squared z raised to 4 times the derivative of y squared plus 72x z squared times the derivative of 0, which makes the whole term 0. So, the derivative becomes 1080 x squared z raised to 4 times 2y with the derivative of y, where dy over dy is 1. Finally, the sixth partial derivative of the function f with respect to y, z, y, and x is 2160 x squared y times z raised to 4.